Good afternoon, sir.
Hello.
Can you hear me, sir?
Yes, good afternoon, madam. I can hear you. Can you hear?
Yes, I can hear you.
Yes, ma'am.
You can share your presentation here.
One second.
Now
Share screen.
we made you co-host. So
Yes, I think now it should be visible.
Yeah, it's coming. Yeah, it's visible now.
Yeah.
It's live streaming on YouTube. So we will be sharing the YouTube link to the participants. After that, we can start.
Yeah, sure, madam. Yeah.
Okay. I'll tell you when we are going to start.
Yes. Okay, madam. Yeah.
Shall we start, sir?
Yes, madam. I'm good to go.
Okay. I'll introduce you, and after that, you can start.
Yes, sure, madam.
Good afternoon, everyone. I'm Ranjini, Assistant Professor, Department of Computer Science and Engineering, Dayananda Sagar University, Bangalore. A warm welcome to the third day afternoon session of Online International Faculty Development Program on Research Perspectives in Futuristic Computing Technologies, organized by Department of Computer Science and Engineering, Dayananda Sagar University. Today we have Dr. Praveen GB, Postdoctoral Research Associate, Division of Informatics, Imaging and Data Science, the University of Manchester, UK, who will be presenting Deep Learning in Medical Image Analysis. Now, I would like to introduce today's presenter. Dr. Praveen GB received his PhD in the Department of Electrical and Electronics Engineering, Birla Institute of Technology and Science, Pilani, India in 2019 under the supervision of Professor Anida Agarwal. His thesis was focused on development of an automated intelligent decision support system for multiple brain disorder diagnosis from MRI scans. He completed his master's degree in the Department of Biomedical Signal Processing and Instrumentation, RV College of Engineering, Bangalore in 2011. During this term, he worked as a project intern under the guidance of Dr. S.N. Omkar in the Department of Aerospace Engineering, Indian Institute of Science, Bangalore. His research is focused on medical image analysis, particularly on applications of deep learning for segmentation and classification. He has published research papers in Elsevier, Springer, IEEE, and he is also an active reviewer of various journals. He is currently working as a postdoctoral research associate in the Division of Informatics, Imaging and Data Science at the University of Manchester, UK. His current research work is associated with Professor Chris Taylor and Professor Ariana Herrick and Dr. Michael Burks in Scleroderma and Reynolds Research Group. I welcome you, sir.
Thanks for the warm introduction, Ranjini Madam.
You're welcome, sir.
Madam, can you hear?
Yes, sir. Yes, sir.
A very good afternoon to and a warm welcome to all my dear participants. Hope you all are doing well and you all are keeping safe. I am Praveen GB, currently working as a postdoctoral research associate at the University of Manchester, UK. So my main research area is application of deep learning techniques for medical image analysis. So as you saw in the previous sessions, Professor Senthil Kumar, he spoke about deep learning sessions, wherein he excellently shared his technical expertise about deep learning concepts. So now, in continuation with the previous talk, I'll be talking about the application of deep learning for medical image analysis. So now, let's begin with understanding what artificial intelligence in a layman language. Okay. So there is a very famous proverb. So we can see here that in learning, sorry, in learning you will teach and in teaching you learn. So that is basically here from this picture we can see that in the left hand side picture, which depicts that a teacher, she is transferring her knowledge to her students. Basically, this is what is happening in the left hand side picture. And in the right hand side, if we are looking at the second picture on the right hand side, here we are seeing that a human, she is transferring her knowledge to the computer. So basically what it means is this is how like we are making the system intelligent, and then this term is called as the artificial intelligence. So now let us move on to the next part. So here, this is basically that we can see in this slide. Over the years, the artificial intelligence has evolved, and which has sub-branched into machine learning as well as the deep learning. So here we can see that the artificial intelligence started since 1950s, and it has been evolving into sub-branches such as machine learning, which evolved at around from 1980s, and then the deep learning, which started since 2010s. So here, by understanding the evolution of this machine learning concepts and then the deep learning concepts, now let us move on to what is deep learning. So here we can see from this diagram that here in this diagram we can see that the basic concepts of machine learning, and then we have the deep learning concepts. So here we can say that the machine learning concept, which means that we have an input image. So in the input image we can see that it's basically a CAD. So here this CAD is from this CAD we will extract the features. As we know that features are the main important parameters or characteristics from this particular input image. So we extract the features from that CAD, and then we feed this particular feature, the extracted features, to the classification network. So here in this classification network, we like supervise, and we know that we have like supervised classification and then unsupervised classification. So here in supervised classification, which means that user knows what are the predicted label, what are the labels, and then we are using that particular labels to teach the network to say that these are the true labels and these are the false labels. So that is basically with respect to the machine learning. And whereas in the deep learning we can see that we have an input image, and then we have the next process, that is basically we have feature extraction as well as classification stage that has been togetherly combined to obtain the deep learning architecture. And then once we have these feature extractions and classification done, so the classifier will give an output saying that whether this particular input image has been classified into whether it's a cat. If it's a cat, whether what type of breed it is. For example, here we are using a cat breed such as like a Russian blue, and if not, then it says it is not a cat. So the main thing that we can see difference between machine learning and deep learning is that here in the deep learning, it's basically the artificial neural networks with many layers basically. So as we keep on adding many layers, so we go deeper into the networks, we can learn better representation here. That is one advantage. And then there are some of the advantages such as here in machine learning concepts, we can see that we have to extract the features. So basically like there are like some of the feature extractors, as we know that there are like handcrafted feature extractions are there. So like handcrafted feature extraction, what happens is a human will look at that particular input image, and then he depicts what might be the features, and then he extract the features from the input image and feed it to the classifier. So for example, if we have to understand this particular concepts in a basic language, so we can say that consider that we have a face of a human here. So we want to say we have a human face, and we want to classify it whether it's a human face or whether it's not. So what we do is like if we have the human face here, so for example, we know that the important parameters of a human face are basically, we know that there are in the humans there are eyes, and then nose, and then mouth. So these are the main features. And what happens is like if we take the features like that, we can say the distance between two distance between the eyes, and then the distance between the eye to nose, and then other features. So these are basically called as the features. Now next, moving on to the challenges in deep learning. So for example, here the main thing that we notice from the previous, that is machine learning and as well as the deep learning concept, is that in the deep learning it's basically the artificial neural network with many layers basically. So the main challenges that we require to train a deep learning is we require a very huge data set. So basically like we need to have a data set of like 1 lakh images or something, so that we can have a better trained network, deeply trained network. So that is one part. The next challenge is the training time is very much huge in when we are considering the deep learning. So basically what happens is like, as in the previous discussion, Professor Senthil Kumar showed that like in the website, he showed that how the training loss and then the validation loss decreases, and it converges at for example at a few epochs. So that is basically the training time. So like if we have like if that particular network does not converge, so basically it's like it's underfitting, or if for example if it is converging at a very early point, so which is known as overfitting basically. So that is one main challenge in the concept of deep learning. Then the other challenges are there are so many parameters which are very hard to interpret. Basically like we have seen like some of the parameters as we saw in the previous seminar, previous discussion, that like learning rate, and then there are like some of the other parameters, those it's very hard to understand like what we need to set. And then the next part is like we have the hyper parameter training, which is a very important stage. So as I said that we have a very huge data set. So if we have to record this huge data set onto the human system on the CPU, it takes too much time. So what happens is like in that scenario, instead of CPUs, so we'll be requiring GPUs to train the huge model. So that is these are some of the challenges. So if we have a very less data set, so it's better to use some of the different like variations by using deep learning. For example, like if we have a very less data set, so we need to augment the data set. So augmenting the data set means that we have to use some of the augmentation techniques such as like rotations, scaling, then translation, shear, and then other scenarios over there. So in that scenario, we can increase the training data set, and then finally we can at least make the training data set to get the means like we are making the small data set to become at least comparatively a huge data set. So for that reason, we require this graphic. We usually use GPUs to train the large data set. So now we have seen what are the challenges that we have in the deep learning. So next part is, now we'll move on to the application of deep learning in medical image analysis. So my main goal or my main scope of this particular seminar will be on, I'll be dealing with how what are the applications that we are using this deep learning in. So here, consider that we have the X-ray image. So for example, as we know, in the medical image analysis, we have like these are the different types of imaging modalities. Imaging modalities means those are the imaging types. So we have, for example, we have X-ray. So X-rays are basically used to understand the structural deformity. So here we can see that X-rays are usually taken, or they are usually taken for to look at the bones or to look at the joints basically. So that is where we are making use of an X-ray. And now the next modality after X-ray is that we are looking at an ultrasound. So here, as we know that ultrasounds are basically used to visualize or to image a very soft tissues structures. So basically here in this image, we can see that this is an ultrasound image, and here we have the right kidney. So basically that we are looking at the kidneys. So the main use of ultrasound is when we are visualizing the abdominal regions. Now, next, moving on to the main imaging modalities that we use are computed tomography and as well as the magnetic resonance images. So here we can see that these both computed tomography as well as the magnetic resonance images, so they are used to view the internal body structures basically. So here we can see that we have the computed tomography. So this is basically an example of an hemorrhage region that is occurring, and then this is an ischemic stroke lesion that is occurring in the magnetic resonance images. So here one thing is like this computer tomography, it uses X-rays to visualize that particular input image, and then in the magnetic resonance we use radio waves, and we analyze that particular input images. And then the main scenario that we see is like the training time, sorry, the time that is used to acquire the cities are very much lesser compared to the ones that we are using to image with the MRI. And then this is less expensive, and we have more expensive MRIs. So here, next, moving on, once we have understood these are the four imaging modalities that are mainly or importantly used in the medical domain. So now let us see what are the challenges. So as we know that if, for example, if a person has some disease, consider that a person is having a tumor. So what happens is like he goes to an hospital, or he goes to a he goes to a doctor. So the doctor will look at the symptoms and other things, and then the doctors will tell him to go to an X-ray, or like for example, if he is having a tumor, so the doctor will tell him to get an MRI done. So what happens is like he goes to an MRI clinic, and then he gets the MRI scans done. So like this is an example of like how it's showing that there are like so many MRIs that are taken for the human brain, and then he gets the MRIs done. So once this MRI is been done at the clinic, then what happens is like then he has to go to the radiologist. Basically, if we are looking at rural areas especially, so one main disadvantage or problems that occurs is like availability of the radiologist. So we know that like in the rural areas there are like very less radiologists that are there. So that is one scenario. And then the another problem that might be facing, that might cause, is the radiologist experience. So as we know that like for example, if you are considering two diseases, so ischemic stroke and then for example stroke and then tumor, so what we can see is like both of them, both of the disease look same for a normal human being. And then if a particular radiologist is very much well experienced, so then he can properly diagnose whether it's a tumor or whether it's a stroke. So that is where the radiologist experience will come into picture. Then the next part is the inter and intra observer variability. So the main thing of inter and intra observer variability means, so for example, we have two persons. So two persons will analyze a scan. So what happens, the person A will say that it is a disease A, and then the person B will say it is disease B. So we can see that how well, like, they are not coming to a same conclusion that it is this particular disease. So like each one will have their own, for example, like analysis. So that is basically the inter and intra observer variabilities. So these are the main problems that are faced when we are looking at the disease diagnosis analysis. So the next part is, now we are moving on to the next thing, that is the challenges here. So what are the challenges? As we know, if we have, for example, if we are looking at this MRI scan, so here we can see that in MRI, we have MRI and CT. The participants who are very well versed with this particular MRI and CT, we know that it will be taken in like three axes. That is basically sagittal axis, then coronal, and then axial axis. So here what happens is, like, we have so many slices for each axis, and then we have different sequences. So that I'll be dealing with in the next upcoming PowerPoint presentations. So here, once we have this particular data, so basically these are the volumetric scans, MRI and CT data sets. Those are very large and very huge. So what happens is, like, if we have to analyze each and every pixels in this particular MRI, so that is very time consuming, and hence, so pixel wise operation becomes very much difficult. So for that reason, some of the things that we can do is, like, we can have a solution such as using a patchwise, as in the previous discussion from Professor Santil. So as he said, that if we have this as the boundary, and we have a human face here, so basically that he mentioned about the strides, and then he mentioned about the padding. Stride is basically that we'll extract that particular patches are basically like for example 3x3 or 5x5, some kind of thing. So those are the patches. Now once we have this particular input ready, the next part is, for example, if we have this data anyways, for example, here we have the MRI data here. So what we need to get is, the next part is, when we are looking at the training particular system, we need the labels for it. Labels means that basically, like, they have to classify whether it's a normal brain or whether it's like it has some kind of like an abnormality, like a tumor or some other disease. So that's basically that we need an annotations for the training data. So this we can get it from the radiologist. So the experienced radiologist will give us this particular annotation. Annotations are basically the labels for the training data. And we know that getting the labels for the training data is very laborious, and then it's very time consuming. So for that reason, what we have to do is, like, if we have a very less data set, in that scenario we can go for unsupervised feature learning by using a very less training data set, and then we can train the model. Or other part is, like, we can use the deep learning architecture. So here, this is the second challenge. The next challenge is, as I said, that we have like CT and MRI. So multimodal imaging means that we use CT and MRI together to obtain a better understanding of what that particular disorder looks like. So in that scenario, we know that some of, for example, if we are considering MRI and CT together, in some of the, for example, in CT, the tumor looks different, and in MRI, it looks different. So basically what happens is, like, it's basically due to the volatile nature of appearance and shape of that particular, for example, tumor that we are taking care or taking into picture here. So this is basically, this can be solved using the image registration technique. So these are the challenges that are faced when we are looking at the disease diagnosis. Next, moving on to the next slide. This is just a slide showing that brain tumor segmentation dataset. So this dataset is taken from the BRATS challenge, which is an which is a publicly available dataset. So here we can see this is a human brain, and then we can see that there are some of the gray patches, and then we have the white patches here that occur. So basically, if we are looking at, this is an example of the brain tumor dataset. So here we can see that if we are looking at an MRI image, we have some of the sequence such as T1 and T2 sequences. So here in the T1 and T2 sequence, we can see in in T1 sequence, we can see it's more of like, it's more bright in color, whereas in T2, it looks a little bit dull. So that is basically because, like, in either of sequence, so the fat and then the water soluble things are like hyperdense and hypodense. So that is the main reason that wherein that we can see the difference between T1 and T2 scans here, these two scans. So let's understand one thing, that if we are considering the brain tumor, we know that if looking at this particular ground truth, the white region represents the brain tumor, and then the grayscale that we can see here, the region around the brain tumor. So this is called as basically edema. Edema is basically a water soluble scenarios or water soluble region around the brain tumor. So if we look at this particular T1 scan, so we can see that there we can see the complete region, and in the T2 scan also we can see the complete region, but we cannot eliminate the brain tumor, exact brain tumor here. So for that reason, if we don't get a proper sequences, then we go for the next sequence, that is basically a T1 contrast sequence. So here T1 contrast sequence is which means that a person, they will inject the contrast agent, that is gadolinium is the contrast agent that they will inject, and then they leave the patient to for some time. So what happens if a person is having a tumor in this particular region, the contrast agent will go and settle over there, and it will brighten that particular region. So here we can see in this three, for example, if we are considering these three different sequences, we can see that the tumor is very much dominant in T1 contrast sequence. For that reason, we are using the contrast agents basically. So this is an example of T1 contrast, and the same thing we have for the for the T2 sequence. So they call it as a flare sequence, fluid attenuated inversion recovery. And then we have the corresponding ground truth for it, with the white as a tumor and then the grayscale as the edema. And then and this is a publicly available data set. So for the people who want to work on brain tumor segmentation, so you can look at the Bratz challenge or Bratz data set, and you can get the you can get the data set and you can start working on it. Now, moving on to the next one. So next one is an example of ischemic stroke lesion segmentation data set. So this is also the same scenario. We can see that we have the T1 data set, T1 sequence and T2 sequence. It looks same. And we can see that there is a stroke that is occurring at this particular ventricle here, which is not clearly visible in T1 and T2 sequence. So here we have something known as DWA. DWA is basically the diffusion weighted imaging. So in the previous one, we saw that it was T1 contrast sequence, and here we have the replacement such as DWA, and then we obtain a stroke region here, and we have the corresponding T2 sequence that is called as the flare sequence here, and we obtain the ground truth, and we have the ground truth also. So the main reason why I'm showing this particular input images are, so next when we are dealing with the analysis, so we need to know like where exactly is the ground truth and how we have to use this particular scenario. So and then for the ones for the people who wants to do a research and who wants a data set, maybe they can look for ischemic stroke lesion segmentation data set, that is also known as ILS challenge. So this was taken from 2015 data set. So each year they have challenges for the open challenges, and you can download the data set and you can check your results with the publicly available algorithms. So now we have understood the data set, two data set examples. Now let us move on to what are the different types of medical image challenges that are available, and then what are the publicly available data sets. So as I said that some of you are interested to do research in medical image analysis. So here getting a data from a hospital is very difficult, because as you know that there are like some ethical issues are there. So what happens is, like if you go to a hospital and then the hospital people won't give the data, because since you know that a person's name should not be revealed in the data, so those are some of the ethics that come into picture. So getting an data set is very difficult from a hospital. And then if we get the data set from the hospital, we cannot validate our results with respect to the previously existing approaches. So comparison wise it becomes difficult. So for example, if you want to look at some of the publicly available data set, these are like some of the examples that I have shown here, around 8 different types of data set I've given. And as Professor Senthil Kumar explained in the previous one, so he showed about the Kaggle data sets that are there, and then he showed about the California, the other Caltech data set. So these are some of the things that I have taken from the Grand Challenge website. So some of the things I can just show fastly, I can skip, is like this is a data set for a brain tumor. As I showed previously that there are like different types of brain tumors are there, in that we have this tumor and we have the edema here. So that is basically the Bratz challenge. And then we have the ILS data set, that ischemic stroke lesion segmentation data set. And then for the, if you are looking at the MRI part, we have 6-month infant brain MRI automatic segmentation challenge data set. And then if you are looking at something like COVID scans, so we have this particular data set and a stare data set for the retina, and so on. So if anyone is interested to look for the publicly available data set, they can go for this particular website and they can have a look at it. So now, once we have understood what are the data sets that are available, so the next part is, now we have to move on to the next one, that is basically the what are the one second. So the next scenario is, we have to look at the image processing methodology. So what happens is, like, once we have an input image, for example, here we are considering an input image of a brain tumor, and then the MRI, and this is an MRI scan. So if we have the input image, the first thing we have to see is, there are like some of the MRI scanners that are available. Like we have GE scanners, then Philips MRI scanners, and then Siemens MRI scanners. So what happens is, like, each one will have their own normalization and intensity levels. So for example, each one will have different like values for their own images. So for that reason, we need to eliminate those particular artifacts from that particular input image. That is done with the help of what is known as pre-processing technique. So here in this pre-processing technique, we can see that if we are dealing with the MRI data set, so we'll use something known as bias field correction. Bias field correction is basically that we are dealing with, like, removing the bias from the MRI scans, and then we are eliminating them. So that is a technique, that is bias field correction, when we are dealing with the MRI. And then we can see here, what I have done here is that we have removed the skull. Basically, this is nothing but the skull stripping, we can see. So we have an input image and we have removed the skull. So this is a skull stripping. So the main thing that we usually do for the skull stripping here is, so if you are just looking at a general image processing methodology, so when we have to just say that where exactly the tumor is occurring, so the main scenario is, we have to draw a line and we have to see the symmetry basically. So for that reason, we use this particular data we use this skull stripping, and then we divide this particular input image into left part and the right part. So what we do is, like, we compare the left region with respect to the right region to see if there are some abnormality that are occurring or not. So for that reason, we are using some of the pre-processing techniques like skull stripping, and then the middle line detection, and then bias field correction, and so on, and the normalization scenario. Once we have this pre-processed image, we need to now look at the feature extractions. So for example, like, some of the, as we know that there are some techniques such as, like, handcrafted features are there. So there are like famous algorithms such as Harlick feature extraction, and then so on. So wherein that they extract the features such as contrast, correlation, entropy, variance, and then the mean and other scenarios from the pre-processed image. And then these features are then given to the either segmentation or classification technique. So for example, here what we have an input image. So if in this particular input image, and this is a brain tumor that is occurring here. For example, if you are just interested in segmenting the brain tumor out of this input image, so we'll use the segmentation technique. So if instead of just segmenting this, if we want to consider whether this is a tumor or not, in that scenario we'll use a classification algorithm. So here let's consider the first scenario, that we are planning to use a segmentation algorithm. Segmentation algorithm, basically, that we have the input image. So in the input image, what we do is, like, we make this middle line detection, and then we see where exactly is the difference in this particular input image. And once we get that once we get the difference here, what we do is, like, there are like some of the famous algorithms are there, such as a fast bounding box. So in the fast bounding box, what we do is, like, we take this particular we draw a rectangle. We draw means basically we get the rectangle out of here from looking at the difference between the left and right part of the brain, and then we have this rectangle that is drawn here. Once we get this particular rectangle, if we have to segment this rectangle, we can see that there are extra parts that are occurring here. So some of the tissues and some of the bony structures are there. So we cannot extract, or we cannot segment this particular hard boundary here. So for that reason, what we have to do, we have to go for an very next approach, that is like a smoother segmentation here. For that reason, we have something known as the active contour model here. So active contour model, as we know, the researcher who are very much interested in segmentation algorithms, they know that active contour model is a semi-automatic method, which means that a user has to give where the user has to give the region of where exactly the tumor is occurring, and then it starts to understand the boundary, exact boundary, like a snake model or a deformable model, and we can get the output like this, the exact structure we can see. So one thing is, since we have this segmentation model here, so rather than having a semi-automatic active contour model, the main thing that we can see here is, since from this fast bounding box we get the boundaries here, so this boundary will be given as an input to the active contour model. So instead of having a semi-automatic, it becomes an automatic method. So automatic method means we have the boundary, and then what happens is, like, using this energy minimization criteria, it understand where exactly are the particular energy minimization criteria, and from the iterative method we can obtain this particular type of structure. That is, this is a tumor that we can segment from this particular input image. So this is for the ones, like if we are dealing with just segmenting it. Segmentation basically is useful. For example, like some of the patients, they have tumor, so the doctors want to take the biopsy of it. Biopsy is basically they do an operation on the brain, on the head, and then they go to the tumor region, and then they remove that tumor part, that is basically the biopsy, and they send it for the analysis to, for example, like histopathology analysis, to see whether it's what type of tumor, like glioma, meningioma, or maybe a benign or a malignant tumor. So for that reason, we'll use the segmentation algorithms. And then for classification is basically like to see whether the particular input image is normal or an abnormal. If it's an abnormal, whether like what type of abnormality, like is it a tumor or is it a stroke or something else. So this is a general image processing methodology that all the researchers will be knowing. So now once we have understood this general image processing methodology, we'll move on to the next part, that is deep learning. So here, let us just take an example of the deep learning here. So here on the left hand side, we can see there are like so many patches of the faces here. We can see that there are like faces of, for example, like five, if we are considering 5x5, there are around 25 faces of different persons here that will be taken as an input. And at the output stage, we want to see that whose exact face is matching, or like, for example, if you are looking at a classification problem. So what happens here is, as we know in the deep learning, each layer, so for example here this is a three layered deep learning network. Here we can see at this first layer we can get some of the features, and at the second layer we can get some kind of like an edge based feature. At the third layer we get a better features. So basically what happens is, like, as we go deeper and deeper into the network, we get the better feature representation. So as we know that, as we saw in the initial slide, deep learning is an artificial intelligence neural network with more layers. So basically here we can see these are the three main layers, and then we have the input, and we apply kind of like a transformation and activation functions here, and we obtain the features here. So at this first layer of the deep learning features, we can see that we are getting some kind of like an just some kind of a patches, and we are getting just some like dots kind of thing, and these are the first layer features. So if we just use this layer and maybe train the model, we will not get the output. So what we do, we go still more deeper again, and here we see that we are getting, for example, here we can see we are getting eyes, and then we get the nose, and we get ears of person.
Sir,
So this is, yes.
sorry for interrupting.
Yeah.
Can you be a little more loud?
Yes. Now.
Yeah, now it's fine.
Yeah. So for example, now here in this particular the next layer, we are getting the better features like eyes, nose, ears, and other things we can see here. So as we go deeper and deeper into the network, for example, in the third layer, we can see we are getting the better feature representation here. So as we keep on going at the next layer, we'll get still more good results. So this is how we are training the network. So for example, we are training a CNN kind of a network. So once we train this network, and we'll feed the test image. In the test image also, it will extract the features like this way, and then at the last layer, it will just classify whether it's it's what kind of face is it. For example, it's a human face or whether it's an animal face or something. So for that reason, this is an a basic example of how deep learning works. Now, next, we'll see that the main criteria of the main scenario or the main thing that we see in the deep learning is it's a convolution neural networks. So convolution neural network, there are like so many CNN architectures that are available. So let us just take an example of AlexNet. So AlexNet is basically used with, for example, a total of 8 layers. So here we can see there are like 5 convolution layers are there, and then we have 3 fully connected layers are there. So basically, what happens is like we have like 224 into 224. So these are the image size. And then we have cross 3. Cross 3 is basically an RGB image. So we have an input, and then we have the convolution filter. So we have 11 cross 11 as a convolution filter, and then we extract the patches across this particular input image, and then we feed it to the convolution layer. We obtain the features from here. And then the max pool operation is basically from this pool. Max pool is like a feature selection algorithm. So wherein that out of the features that we have extracted from this convolution layer, we'll see which are the main features. So that is how we do. And then finally we end up in like some features like 4096, and then again 4096, and then finally we end up in features such as like 1000 features. So this is how an example of a convolution neural network works. And then this is a basic example of AlexNet, so that we use in the image processing examples. So now, after understanding the convolution neural network, the next part is this deep learning is mainly used for like as we know, there are like some problems such as regression problem, segmentation problem, and then the classification problem. As you saw in my slide about general image processing methodology, I showed an example of segmentation, wherein that we segment the tumor out of that MR region, and then classification problem, whether we say that it's a normal image or whether it's an abnormal image. So these are these are the two problems. And then there is another problem such as a regression problem. So as Professor Senthil Kumar told in the previous talk, that like for example, if we are looking at the regression, we have like logistic regression and then the linear regression models. So here the main scenario of regression is, for example, if we are considering a basic example, so we say that now in the year 2020, for a site of 3040, it is costing, for example, like 10 lakhs. So in 2025, we have like 10 lakhs will become 20 lakhs. So like that, we have to predict the site prices for in the for the year 2022. For that reason, we have something known as regression problem. So the main scenario of regression problem when we are dealing with the medical images are, one is vessel width estimation or blood vessel prediction. So we have the, for example, if we are looking at the retinal images, we have the retina of the eye, and then we'll have the blood vessels in that particular retina. So basically what we have to do is like we have to segment that particular blood vessels. So that is basically a regression, an example of a regression problem. The next one is segmentation. As I showed in the slide, it's either like brain tumor segmentation, or maybe if we are looking at the stroke lesion segmentation, so we can use deep learning. The next part is like we can use it for a classification task. For example, if we want to classify the tumor region into its subtypes like meningeal, malignant or benign, so we can use deep learning for that. So these are the three problems. Now let us take an example of each type of problem and see like how deep learning can be used. So this is an example for a regression problem. As I said that this is an input image. So in the input image, we can see input image is taken from, like for example, it's an fundus images. So in this fundus images, we have the retina, and then we can see that there are some of the blood vessels that is occurring here. So if we look at this particular input image, the doctor or the radiologist has given the labels for here. Labels is basically a black and white image with the blood vessels. So vessels. The main idea of this particular using a regression problem in deep learning is that we have to predict this particular vessels basically. So as we know that if we have to just say that whether tumor is present or not, so it's a classification problem. So if we have to just segment this particular, if we have to just remove this particular blood vessels, it's a segmentation problem. But whereas here we have to predict where exactly the blood vessels are occurring. So for that reason, and this is a paper that was published in 2018 by Sergio Pereira et al. Group, wherein that what they use is a convolution neural network architecture here, fully convolution neural network here. So what they usually do is they take the input image and then they take the label image or the ground truth for that. So they use a wavelet transform here, and then they extract the wavelet transforms here at this particular stage, and then they concatenate the output of this wavelet transform stage as well as the input here. And then what they do is like they extract the patches are basically they extract like for example, if we have 256 by 256 image, patches are basically that if we are dividing then input image into 4 different quadrants, we say that 256 by 256 basically we get as a 60 I think 128 by 128. So like 128 by 128 will be one patch size here, and then again here. So like for that reason we'll have 4 different patches. So that occurs in the patch extraction criteria. After that, what we have to know is, as I mentioned about data augmentation here in this scenario, they are using a rotation data augmentation. Why they are using the rotation data augmentation is, if we have since this is a regression problem, we for every different image we see that the blood vessels sometimes it occurs here, and in the some of the scenarios it occurs at different locations. For that reason, we have to see we have to rotate this particular input image in all direction so that we get labels for that. When we are using that particular test image, we should not miss out any of the labels for them, means the predicted labels for that. So we use they use data augmentation here, the rotation data augmentation, and then they feed it to the fully convolution neural network here. So as we know from the previous presentation, Senthil sir spoke about the loss functions. So what we do is like we have the labels, the ground truth labels, and then we have the fully connection neural network here. The whatever the logics that occur after the fully connection neural network layer, both this prediction and as well as the labels we feed in. So basically this is prediction and then this is the label. So we subtract here and we find the difference. So basically if we are looking at the regression problem, the main thing that we are looking at is the mean square error. So mean square error loss function we use here to see what is the error, the difference between the predictions and as well as the input. So for example, if we get a loss function of like 1, which means that the value is very much higher. So what happens again, it back propagates to the network, and again it keeps on back propagating till this particular the value of like validation loss of 1. Sorry, and the loss become from 1 becomes very much lesser, like 0.00 something. So that is basically that is occurring at each stages, and then this occurs with the in each epochs basically. So once we do that, and once we get the least loss function, least loss values, so which means that we have trained the model basically, which means that the model has converged properly. So those particular model, we take the weights of that particular model and we just save it. Now moving on to the next part, the next is testing. So here we have trained the model. Now we are going to test that particular input image. In the testing, we again use the wavelet transform and we concatenate whatever the wavelet transform output we are getting with respect to the input. We extract the patches. And here we can see that these are the multiple predictions. Here we use the transformations are basically whatever that we have done from the previous one, rotation, and we use the same fully connection neural network here with the weights here. And once we get that, so whatever rotation we do, we again do the opposite rotation, so that what happens, we are aligning it again back to the normal scenario. And once we have this particular here, we get the output at this layer, and we align and we synchronize with whatever the rotations we have done. And at the end stage here, we get the output. So once we get the output, we have to as we know that we have we have best prediction and then we have the worst prediction. So in that scenario, we should take the average of it. So average is basically here we are taking kind of like a mean predictions. So it's basically an output averaging, and then we get the final output, such as like we can see that the blood vessels are properly visible. So we can see we can correlate this input with respect to the output stage. So this is an example of regression problem for a deep using deep learning. So next part is we'll move on to the next scenario, that is segmentation problem using deep learning. So here this is basically there are tumor regions that are occurring. So this is a brain tumor segmentation using a convolution neural network. So here we can see that it also follows the same scenario. We have an MRI input images. We have the training labels for that MRI input image. What we do is like we take the input image as I showed in the scenario, that we first pre-process the MRI input images. So once we pre-process the MRI input images, we extract the patches. So as I mentioned about the challenges, if we are looking at the pixel wise pixel, so it is very tedious and it's very huge. So for that reason, we go for what is known as the patch-wise extraction, which is, as you know, that it's very famous approach, and like it depends on like how we want to extract the patches. So once we extract the patches, again we pre-process those input patches, and then after that we feed it to the convolution neural network. So once at the same in the from the previous slide, we could see that we feed the labels, whatever the labels, to the loss function, and then again we get the loss values here. So once we get the least loss values, so that is a network which has the which is the best model. So we call it as the best training model. And then we feed the test data set, and we follow the same architecture: MRI pre-processing, patch extraction, and then patch pre-processing. This stage is very much important because, for example, if you are looking at a transfer learning or something, what happens is like if we have got this model from say for example from some of your friend, and if you want to test your model, so what happens is like you should use the same mean and variance for this particular patches. For that reason, we should know these what are the pre-processing values that they have used, and so that if you use the same values and if you try, test their network with your test inputs, so you can get the very good results. So here we get the CNN output, and some of the post-processing techniques are used so that we can exactly get the tumor regions. So here we can see that this is an example of segmentation problem in the deep learning. So now we have understood the regression and as well as the segmentation problem. Now we'll move on to statistical. We'll move on to statistical measures for evaluating the performance. So here in this, as I mentioned, that there are three problems. That is, one is classification, regression, and segmentation problems. So if you are looking at the classification problem, some of the statistical measures that we have to always keep in mind is that we have to look at accuracy. So if we are saying that we have a classifier model, we say how much accurate is it. And then the next part is the main statistical measure we should see is the area under curve. So here this is called as rock curve. The rock curve means receiver operating characteristic curve. So here this is an example wherein that we have false positive rate and true positive rate, which means that sensitivity versus specificity, and we have the threshold for here. So these are some of the two different test data I have done. So here we can see that whatever the area that is occurring inside this particular region is called as the area under curve. So that is one of the main characteristics, because to say that how well is your model has trained properly. Because for example, if you get for example, there are some reasons wherein that some people will be getting an accuracy of like 99%, 100%, but whereas their model will fail when it comes to area under curve, because just using accuracy as a classification statistical measure will not prove whether how well your model has been trained. Then there are other scenarios such as sensitivity and specificity that we should keep in mind. So this is with respect to the classification approach. And when we are looking at the regression, as we saw in the previous the retinal image the regression problem, so we could see that as we know that regression is basically at each different interval we have different values. So here there is one famous this one plot, or we can call it as a correlation plot, wherein that bland Altman plot. So whenever if any of you are using or doing an experiment on regression, So the best thing that you can use is you can use a correlation plot to show your output. So here we see that these are some of the apex widths. So this is the ground truth widths that the doctor has given, and then these are the predicted widths that we have found. As Professor Senthil Kumar said that y is equal to mx plus c. Here, this is the line, the slope of the line. So 0.82. So what we can see, we can see that there is a dotted line that is occurring diagonally here. So and then 0.82 m is nothing but the slope. So 82 is the slope. 82, this is the slope of it. So if this particular slope becomes 1 here, we say that we have got a very good predictions. So r square is nothing but the correlation value here. So we say that 78% of the values have been correlated here. Still there is an space for improvement. So we'll just like quickly see an example here. For example, if we are considering this point here, this is an vessel width estimation. So if we are considering this point here, so the ground truth, the doctor has given the ground truth value of somewhere around 90 or 95 as a vessel width pixels, and we have also detected as the 95 as the vessel width. So that is how we predict, and then we say that this is how good is our this the accuracy or the correlation values for the regression problem. And then the last part is, if you're looking at the segmentation problem, there are two important parameters. That is, one is Dice coefficient. Basically the ones, the researchers who are very much into the image processing and segmentation problem, they'll understand what is Dice coefficient and Jaccard coefficient. Those are basically that we have an predictions, and then we have the ground truth. We overlap one upon another and see how much is the region coincides with the ground truth, and then we get the Dice coefficient. So these are the main statistical measures that you have to always keep in mind when you are evaluating the performance of a your the CNN or maybe a machine learning or a classic any models. Now, till now we have looked at the deep learning approach. Now let us just have a picture about what is unsupervised feature learning approach. So for example, if as I mentioned that if we want to work on deep learning, the one criteria is we need to have a graphical processor units, because we have the very huge training data set. So when we have the training data set, the just a local computer or a local laptop, means personal laptop, it cannot have that much computational power. In that scenario, if we don't have a GPU cards, so we cannot use deep learning. In that scenario, one easiest approach that you can think is an unsupervised feature learning approach. Or the meaning of unsupervised feature learning is it's same like a data as a dimensionality reduction technique or maybe a reconstruction scenario. So here we have an input image, and then we have a reconstructed input image. Reconstructed input image means we have this input image, and we need to have something in middle, such a way that we can reconstruct whatever the input image that we are feeding to get the output image. So this is basically an unsupervised feature learning. We don't know what are the features, and we are telling the yeah, model, or we are telling the approach this particular black box here, to say that we need to get the reconstructed output same like this. So there are two main approaches. The one is k-means sparse coding, that's a clustering approach, and then another is a stack sparse autoencoder model, which is a dimension reduction technique. So I'll just show some of the results for that in the next slide. So as I mentioned here, this is one important slide you have to see here. So this is basically a traditional machine learning approach, and then we have an unsupervised feature learning approach. So the main difference that we can see from the traditional approach and as well as the unsupervised feature learning approach is, here we are extracting the patches, and we are designing the features here. So we can see here, for each image we are saying that these are the features that you need to extract. Whereas here in this unsupervised feature learning, we are extracting the patches, and then we are going for the k-means filter learning approach. What we do is like we use these particular patches, and then we build a filter bank. So from this filter bank, what we do is like we encode the filter bank, and we obtain the features basically. So everything is occurring at the unsupervised manner. So we are not doing anything over here. And at the last stage, we'll supervisedly train the classifier. So basically, it's an unsupervised feature learning plus supervised classification approach. So it's that is how this thing I can tell. And here, as you can see that this is how we have built a model. And if we are looking at the testing phase, in the testing we get the testing input and testing images, and we extract the features when we are looking at the traditional machine learning approach, and we feed it to the classifier will say that what exactly is it. So here we are taking this particular lesion here, and we are giving it to the trained classifier model. It gives us saying that it's a detected lesion. And whereas the difference here, we can see the difference here again, we are extracting the same patch and we are giving to the encoder. So the encoder automatically will check this particular filter bank. It will extract the features from that, and it will give the testing features without a human interaction. And then from this testing features, we are using this classifier model, the trained classifier model, and then we get the output and we say that it's a detected lesion. So this is how we can say that we can differentiate between the traditional machine learning approach and then the unsupervised feature learning approach. So now next, moving on, as I mentioned that we have to extract the patches and then we have to concatenate the patches. So here we can see that we have extracted some patches here. So these are the normal patches that are happening from 4 different slices of sequences of MRI, and then these are the abnormal patches. So we can see that everything is concatenated here, and then it will be fed to the neural network, which will train the model. And then finally we can have this particular for example, if we are taking these patches, it will look for this filter banks here whether it is occurring or not. If it is occurring, then it says that it is occurring, and then it will give us the detected lesions. And then these are some of the examples here. We see that these are the first column depicts the input image, and then the second column is basically the ground truth that radiologist has given. The third column depicts the probability map or the reconstructed input that we obtain from the particular unsupervised feature learning approach. And then what we do is, like, once we get this particular reconstructed input, we use a segmentation technique. That is basically we can use just a thresholding technique, threshold the values. That is for example, these are white regions, so anything that is less than 200 or 250, you can eliminate it, so that you will get only the white region here. And this is how we can extract the for example, tumor region here, sorry, ischemic stroke lesions here. And here we can see we have like white region, we have the green region, and then we have the pink region. White region is basically those are the true positives here. True positive means these are the these are the abnormality that we have detected, and these are the which is occurring in the ground truth. So these are the truly detected ones, the white ones. And then the green ones are those are the regions, abnormal regions that are there but we have not detected. And then the pink region or the maroon one we can see here are the ones that we should very much we should be very careful, because those are the false positives. False positives are the ones that are not there in the ground truth, means those are not the abnormal tissues or abnormal patches, but we have detected from our approach. So if we are looking at the our any like classifier model, we should first look at the false positives. So we have to eliminate the number of false positives, and we should have more true positives. That is how we get the better results. So this is with respect to the k-means clustering approach. Very quickly we'll see the stack sparse autoencoder. In the stack sparse autoencoder, here, as I said, that it's a in stack sparse autoencoder, we know that it's an reconstructions that is happening. So as I showed in the initial image, and we have the reconstructed output. So I had put a question mark, which means that what is occurring at that intermediate stage. Here we have x1, x2, x3 are the input values, and then we have the bias represented by the b. And then we have w and w1 and w2, which means that weights of that particular first layer, and then weight output of the hidden layer. And then h1 and h2 are basically the number of hidden neurons in the hidden layer. And then again we have the b, and then we have x1 cap, x2 cap, and x3 cap, that represents basically the reconstructed output from the input. So this is how an basic autoencoder that occurs, that works. And then a general idea is, as I spoke about the deep learning, as you saw that at each layer, when we saw an example of the face recognition task, so we could see that at the first layer we could get just basic features. At the second layer, we could see that the person's eyes, nose was visible. At the third layer, the complete face was visible. So that is how we go deeper and deeper, we get a a better network. So that is why what we do is like, this is a single hidden layer. So if we add more and more layers, and if we are stacking one upon another, so we call it as a stacked sparse autoencoder framework. So the main scenario is, we have the input images, input patches, and then we have the different hidden layers. And at each hidden layers, we could see that the number of hidden, for example, h1 to hs, so we can see that number of hidden neurons decreases. Basically, what we do is like, we get some of the loss values here, so we get still more less loss values. So what we expect is, at the end of this third stage, we should get a very much less loss values. Loss values are basically whatever the labels are there and whatever we have predicted, so the difference between those are basically the loss values. So once we get the very less loss values at this part, we take that, and then we use a supervised classifier, that is an support vector machine classifier, to train the model. So once we train the model, the stack sparse autoencoder model, yeah, so this is a complete schematic diagram. So as I mentioned that we have training data, we have the training ground truth. So this left part is the training section. We extract the patch, pre-process the patches, and then we use data augmentations for that. And we have like autoencoder 1, 2, 3, as I showed in the previous things that we have. These are the different autoencoders. We stack each one upon another to get the stack sparse autoencoders, and we get the training features. So till here, this is the unsupervised feature learning approach. So if we don't have a deep learning scenario, or if we cannot use convolution neural networks, so maybe we can one replacement is like, you guys can think about using a autoencoder model, wherein that you can get the features out of here, and maybe you can train the model in a supervised manner. So here we are using the svm classifier and building this stack sparse autoencoder. And when we have the testing data, we extract the patches, pre-process it, and feed it here. So we get the output of here, saying that whether a tumor is present or not. So if it's not present, then we say it as a normal image. And if it is present, then we say again, see that what exact type of tumor it is, and then we segment it. So again, we need to look at the features and classify whether it's meningioma or glioma or a different type of tumor, and then we should segment that particular tumor region. So this is an example of a tumor, as I showed in the stroke segmentation also. This is an input image, and then this is a label that radiologist has given, and then this is the segment, the predicted output that we are obtaining from our approach, and we have overlapped on it to see that how well our approach matches with respect to the ground truth. And then, as I mentioned, when we are looking at the for example, the segmentation approach, we'll look at the dice coefficient. So we can say that our approach has 88% kind of a dice coefficient, basically, which means that 88% of this region, if of this particular region is occurring at this the ground truth. That is how we call it as the dice coefficient. And then we have the other parameters. So as I said that, we can see that area under curve is 87%, and we are obtaining an accuracy. So in this scenario, we'll just not look at accuracy and say that we have got a less accuracy. The one good thing is, we can show with respect to the dice coefficient, and then we can show with respect to the area under curve, and maybe sensitivity and specificity also. So this is about unsupervised feature learning approach. So my suggestions about the researchers that you want to use deep learning are, so if you have a medical image segmentation task, so I suggest you to try unit architecture, because unit, as I have used some of the architectures, I felt unit was very easy and very it was giving a better results. So if you are looking at the segmentation task, so for example, if you are looking at a regression or a classification task, so I suggest you can use a basic layer, basic network such as ResNet or VGGNet. Since as you know that VGG have 19 layers, and then ResNet has 18 or 34 or still more. And then the one more thing that you have to use is, like, if you have less data set, use more data augmentation techniques, such as I mentioned, rotation, translation, scaling, shear, and other things. so you can get more data training, means the true samples, and then you can improve the performance. The other part is like transfer learning. So transfer learning is basically, if for example, if one of your friend has worked on some research domain, means if you both are working on the same research domain but on a different problem, so if he has got a very good data, that is a model, a trained model, so you can use that particular trained model for to train your approach. So that's basically you are pre-training your model, and then you can fine tune your model for your approach. Or if you don't have that, if you both are working in a different domain, maybe you can train from the scratch if that is not possible. The two more important part is better to visualize the intermediate outputs. So what happens is, like, if you are using the data augmentation technique, sometimes we might go wrong at this data augmentation technique. So my suggestion is you visualize the output and input after the data augmentation technique and data augmentation stage, and then after which you look at this consecutive stages like filtering stages to see like what are the weights that the model has learned. The last point is pre-processing of the input is very much important to train a model. If you have not properly normalized an input image, so maybe you might not get an exact, I mean, the required results. So these are some of the suggestions, and then some of the reference materials that in the previous say, in the previous talk, some few people were asking about like what are the good materials. So maybe you can look at some of the things like online YouTube link is there. So Stanford University, they have an course, online course on convolutional neural network for visual representation, which is good. And then if you're looking at a specialization courses, so Andrew Ng has specialization courses that you can find it on the Coursera. So I concluded my talk. So any questions?
Thank you, sir, for sharing your knowledge and applications of deep learning in medical image analysis and
Yeah,
making the session more interesting.
yeah. Thank you, ma'am.
With your permission, we can move on to the questions from the participants.
Yeah, sure.
I request the participants to post your questions on the chat box on YouTube. So there is a question.
Yeah.
Based on medical image data sets, how to decide whether to go for supervised or unsupervised learning?
Yes, ma'am. So, like one scenario you have to see is, for example, if as you know, supervised means that you have the training data set that is available. So, yeah, unsupervised means that you don't have a training data set. So, if you have very good training data set, or the labels, if the radiologist is willing to give you the labels for it, then maybe you can look at the supervised classification or supervised training. So if you don't have a labels, so you can use unsupervised feature learning. And then one more thing that you can think is, there is something known as semi supervised learning, wherein that if you have a like not too much huge too much huge labels, or if you have very less labels, in that scenario you can make use of the semi supervised approach. So that's basically like a pseudo labeling. You can check it on internet. There are some of the papers, the recent papers, so they work on that.
Thank you, sir.
Yeah.
Another question is, in MRI, what do you mean by slices?
Yes.
Which
See.
which one more is the in addition to that, which slice should we work with when we do multimodal fusion?
Yeah. See, that's a good question. See, basically, what I meant is slices means. So, if you are looking at an architecture of a house, so we see that from the front side, we see the home as a front side. So if we are looking at from the top angle, so we get the home as a means the home or the flat or a building as a different view. So what happens is like, if we are take, as we know that in the MRI there are so many magnet and then there are so many sensors that are available. So what happens is like there are like rings of sensors that are available. So every time it keeps on moving. So if we are taking an MRI, so it will be taken with the help in axial plane, sagittal plane and coronal plane. So basically, which means that at the top angle, at the front angle and at the back side. So these are the different planes that occur. And then what other scenario is, as I mentioned about slice means, so slices are basically, if you are very well versed with MRI, so we know that what is known as T1 relaxation times and T2 relaxation times. So basically, for example, if I say that I am at point A at time 0, so if I move to point B at time 1, which means that there is a difference over there. So what means that it slices means at each different time intervals we get different images basically. So slices are the images that are acquired at different time intervals. Those are the slices. And the second part of question, your question was, so if you are taking an axial plane, or for example an axial plane of MRI, and if you are taking if you have to register that with multimodal imaging technique, so you have to take the axial plane of that other model also, and then you have to register, so that you can have better structural and functional visualization of the particular like organs or something that you are looking at.
Thank you, sir.
Yeah, thank you, ma'am.
Um, we have a question. How many CT images to be considered for prediction analysis?
Yes, ma'am. So, like, there is, for example, as I said, that it depends on what exactly you are looking at. Like, if you are planning to work on, for example, a supervised classification, or just a machine learning approach, maybe for training a city model, as you know that one of for example, if you take a volumetric CT or MRI images, so one patient's one scan will have 180 images in one plane. So you can imagine, so as I said that there are four T1 T2 flare and the other was T1 contrast. So 180 into 4, so on approximately you can say that 200 into 4 is 800 slices, 800 images you get for a one patient. So 800 will be a data set for a single patient. So like that, if for example, if you have 10 patients data set, so you have almost 8,000 images. And then once you have these particular 8,000 images, since if you are working on the patch based approach, so you will get, you can, out of 8,000 images, maybe you can get like 80,000 or maybe even like 60 1 lakh 60,000 patches. Those are the number of patches you can extract. And as I mentioned that if you are using data augmentation, I think you can get the better results. So it's there is nothing such as like these are the number of things that you should keep in mind. One thing is like I for example, if you have 10 scans also, if you use better data augmentation technique, it will be very helpful for you people.
Thank you, sir.
Yes, thank you.
One question is, and how do we certify that our method for fusion is better than other using subjective analysis?
Yes. So as you know that this is basically a registration problem. So if you are looking at the fusion, so basically what you are doing is like you are taking an input image and you have, for example, you have two input images from different, one is from CT and another might be from MRI. So you have to look at the positions of where exactly it is occurring, and then you have to fuse it. So as you know that if you are looking at the registration technique, there are something like rigid body registration, then affine transformations and other things. So basically you have to look at what exactly you are looking at. The other easy criteria can be like you can have an atlas guided registration, wherein that you know where exactly that particular this is the human brain. And so that when you take the your own image, so you know that where the human brain outer structure you will be knowing, where exactly the inner region that you obtain from your approach, you can just fuse it on that particular atlas model, and then you can correlate your results correctly.
Thank you, sir.
Thank you, ma'am.
And one participant has asked, can you explore about database for lung cancer CT images?
Yes, as I mentioned, I'll just show you. Is the screen visible, madam?
Yes, sir.
So here, as I mentioned that, as I showed in my slide, that grant challenges website is there, wherein that you get the publicly available data set. So here you can see that there are like so many different approaches you can find. Maybe there it might be helpful for you to look at maybe chest CT scans here. There are like here we can see, I think somewhere I saw that. Yes, here you can see that they have worked on something pneumothorax segmentation, and then there was something on COVID segmentation also. So maybe you can have a look at this website. It might be here you can see that CT diagnosis of a COVID-19, and then there are other challenges are there.
Thank you, sir.
Yes, thank you, ma'am.
Thank you so much for clarifying the doubts.
Yes, ma'am.
Thank you for sharing your time with us today.
Yeah.
Now, I
Uh,
request the participants to fill the feedback form. The link will be shared to the chat box on YouTube.
yeah. I hope this session was very informative to all of you. I would like to thank all my participants for being a part of this session. And I would like to sincerely thank Dr. Shaman, Professor Ranjini, and Professor Mauli, and all the organizers from the Computer Science Department, the Anand Sagar University, for giving me an opportunity to share my insights on deep learning in this forum. Have a lovely evening, all of you. Over to you, Ranjini Madam. Thank you.
Thank you so much for accepting our invitation and to be part of this FTP.
Yeah, thank you, Madam.
Uh, the feedback link will be shared soon. Please fill the feedback for getting a certificate to the registered email IDs. Once again, thank you all for joining us today. Have a great day. Thank you.
Thank you, ma'am. Bye.
Bye, sir.